Let's talk about how corresponding parts of similar triangles are proportional. That might sound kind of familiar to something we learned in first semester, which is that corresponding parts of congruent triangles are congruent. But since this chapter we're dealing with similarity, we're going to say that the corresponding parts are proportional, not congruent. But first, let's learn some new parts of triangles. First is a median. A median is a segment that connects a vertex of a triangle to the midpoint of the opposite side. So in this diagram, AM is a median of triangle ABC because it goes from vertex A across the triangle to the midpoint of side BC. Now you might be saying, well, hold on, I thought we already had a thing that connected midpoints of triangles. And we did. That was called a midsegment. We learned that a couple videos ago. But a midsegment connects two midpoints. So M is the midpoint of BC, and if we knew the midpoint of AB, we'll call it N. N to M would be a midsegment because it connects midpoints. A median connects one midpoint to the vertex on the opposite side of the triangle. We also have angle bisectors, which we've actually already learned what an angle bisector is all the way back in Unit 1 at the very beginning of the year, but this time we're going to specifically say it's an angle bisector of a triangle. The idea is still the same though, that it's a segment that cuts an angle into two congruent angles. So AD would be an angle bisector of triangle ABC because it bisects angle BAC. And we have altitudes. An altitude is a segment that connects a vertex of a triangle to the opposite side so that the segment is perpendicular to the third side. So AE in this diagram is an altitude of triangle ABC because it connects vertex A to side BC in such a way that those two segments are perpendicular. These three segments look a lot alike, so it's really important that you actually look at the information that you've been given on your diagram to identify which type of segment you're looking at, because it's not very easy to tell which one is which just by looking at where it is in the triangle. As you can see, altitudes, angle bisectors, and medians look a lot alike when you all draw them on the same diagram. So instead, look for the bisected angles if it's an angle bisector, the bisected segment if it's a median, or the perpendicular segments if it's an altitude. We're going to use the fact that corresponding parts of similar triangles are proportional to solve for the lengths of medians, angle bisectors, and altitudes. And basically all we're doing is adding an extra ratio onto the statement of proportionality that we already know how to write. We learned earlier this unit that if you have two similar triangles, like how ABC is similar to PQR, then you can compare each of their pairs of corresponding sides and write it as a ratio. So all we're doing here is adding an extra ratio comparing, in this case, the medians of these two triangles. When you reduce that ratio, it should be the same scale factor as the other three ratios. And I could write a similar statement comparing the altitudes or the angle bisectors of these triangles as well. So let's put this knowledge to use. I know that triangle NOP is similar to triangle RST, and we're supposed to figure out the value of x, which is the length of UR. Well, in this situation, we've actually been given medians of these two triangles. I can tell that NQ and RU are medians because they connect a vertex of the triangle to the third side so that it bisects that third side. Q is the midpoint of OP. And I can tell that these are corresponding medians. N is the first letter in the first triangle's name, and R is the first letter in the second triangle's name. Those vertices correspond. And I connect it to side OP, those are the last two letters, and I connect this to side ST, those are the last two letters. So these medians are corresponding. And also, NP is the side that I know, that's first and last letter, and RT is the side that I know on the larger triangle, and that again is the first and the last letter. So I know that these four lengths that I've been given are corresponding parts of similar triangles. So I can set up this ratio, x over 84. So that's the longer median over the shorter median is equal to 91 over 78. So that's a side length in the larger triangle over a corresponding side length in the smaller triangle. And now I can just cross multiply to solve. X times 78 is 78x, and 84 times 91 is 7644. Divide both sides by 78, and we get an answer of x equals 98 meters. And as we said, these two segments are called medians. Let's try another one. Well, in this case, we've been given angle bisectors of triangles. I can tell that GJ and GK are angle bisectors because of these angles that are marked as congruent. GJ bisected angle EGF. And I can verify that these are corresponding angle bisectors because they both go from G to the opposite side. And G for both of these triangles' names is the last letter. And it connects it to EF, which is the first two letters, and HI, which is also the first two letters. So these two angle bisectors are corresponding, and these two side lengths are corresponding as well. G and E are the last and the first letters, and G and I are the last and the first letters. So these two sides correspond. So I have corresponding parts of similar triangles, which means I can set up a proportion to solve for the missing length. So I will write x over 18, that's the yellow triangle's angle bisector, over the green triangle's angle bisector, is equal to 28 over 42. That's the yellow triangle's side length over the green triangle's side length. Cross multiply and solve. X must be 12 inches, and those were angle bisectors. We've got a pretty crazy looking diagram on this next one. We've got lines all over the place, and we have some right angles labeled. So that tells me that these must be altitudes because each of the segments inside these triangles are perpendicular to the third side of the triangle. It's helpful on such a crazy looking diagram to identify which triangles it is that you're talking about because there are like so many different triangles in this diagram. So what are we actually doing here? Triangle ABC, ABC, so that's the whole triangle. And triangle DEC, DEC. So that's like this bottom part of this whole big triangle. So looking at the altitudes that I have drawn in each of these triangles, let's make sure that they're corresponding first. One goes from B to the opposite side, and one goes from E to the opposite side, and B and E are both the middle letters in each triangle's name. And let's see, B goes to side AC, the whole thing. A and C are first and last, and E connects to side DC. D and C are first and last. Okay, cool. So these altitudes are corresponding. Now let's look at these side lengths that I've been given. Well, 16 isn't actually a side length of a triangle that I care about, but 80 is. 80 is one of the side lengths of triangle DEC. So we need a corresponding side length on triangle ABC. Well, I could figure that out by adding these two lengths together. The corresponding side length to 80 would be 96, because 80 plus 16 is 96. Okay, so let's set up our proportion. X over 50, so that's big altitude over little altitude, is equal to 96 over 80. So that's big side length over little side length. Cross multiply and solve, and we find out that x is equal to 60 centimeters. And these were altitudes because they were perpendicular to the third side. On our next diagram, we actually have two different variables to solve for. Looks like we're working with medians this time because this segment bisected each of these sides of the triangles. We've got two triangles built within each other this time. I'm dealing with triangle PST, so that's like the top 2/3 of my diagram, and triangle PQR, which is the entire triangle in this diagram. So those are the two triangles that we're told are similar. And we need to solve for x, and we need to solve for y. Well, let's start with x. X is part of one of the medians. 42 is the smaller median, but 42 plus x would be the bigger median, because I have to go all the way from P across the triangle to the third side. If I'm talking about triangle PQR, the third side of that triangle would be QR. So it's not just 42, and it's not just x. The larger median here is 42 plus x. Now I need to compare it to corresponding sides that I know both lengths of. But 18 isn't actually a full length. 18 is just from S to N. But since N is the midpoint, we would know that this side is 18, and since M is the midpoint here, we would know that this side is 27. So actually this whole side length is 36, and this whole side length is 54. Okay, so let's set up our proportion. X plus 42 over x. That's the larger median over the shorter median, is equal to 54 over 36. That's the larger side length over the smaller side length. Cross multiply. Don't forget to distribute. That's not just 36x plus 42. It's 36x plus 42 times 36, which is 1512. And that's equal to 2268, which is what you get when you multiply 42 and 54. So subtract 1512 and divide by 54, and we find out that x is 14 feet long. Okay, cool, but we still need to figure out what y is. Y is a side length of the smaller triangle, and the corresponding side length on the larger triangle is not just 30, it's y plus 30. So my first ratio, I'll write smaller side length over larger side length, and I'll set that equal to, well, no reason to reinvent the wheel. I used 36 from 18 and 18 put together and 54 from 27 and 27 put together to figure out x, and I can use that here too. Just make sure that you're writing it in a corresponding order. Since I did the smaller triangle on top this time, I need to again put the smaller triangle's number on top for my second ratio. Cross multiply, I get 54y equals, again, don't forget to distribute, 36y plus 1080. Subtract 36y from both sides, and divide by 18, and y is 60 feet. And that's all you need to know about using corresponding parts of similar triangles to calculate missing side lengths. In our next lesson, we'll learn about a non-isometric transformation called dilations, and we'll learn how that relates to similarity.